So this is operated at 575 degrees C. So 575 degrees C, that's pretty high temperature, and 248 atmospheres. 248 atmospheres is extreme pressures. And so extreme temperatures and pressures are required to get this reaction to go. It's a very difficult reaction to get going. How many liters of nitrogen measured at these conditions? And so what we're after is the volume of nitrogen. Measured will react to produce 9.16 times 10 to the third grams of ammonia. So here we got 9.16 times 10 to the third grams of ammonia. So about 9,160 grams of ammonia. So how many liters of nitrogen are required? So there's another way I do stoichiometry maps as well. Let me show you. One of the other ways I do stoichiometry map is just have it based on the equation. So basically, what we're going to do is we're going to start off with grams of ammonia here, and then that's what we're given, and then we go to moles of ammonia, and then from moles of ammonia we go to moles of nitrogen. So we can figure out how many moles of nitrogen there are, and then we have two methods here. We can use the ideal gas law. That is, the volume is equal to nRT over P, where we just solve for N. N is the moles of nitrogen. So we could get the volume of nitrogen. Or two, we could use the molar volume method. And that will end up at liters of nitrogen. Yeah. So let's go ahead and do this one then. Let's see what we get. Which method? Use molar volume or ideal gas law? Do you have a preference? Molar volume. And usually I use the molar volume. Let's go ahead and calculate the molar volume under these conditions. The molar volume is the volume per mole, which is going to equal within RT. This is going to be RT over P. So R, 0.08206 liters times atmosphere per mole is Kelvin. T is 575 plus 273. What is 575 plus 273? I'll just do it on the calculator since I don't want to think about it. 848. 848 Kelvin. Divided by the pressure. The pressure is pretty high, 248 atmospheres. 48 atmospheres. Atmospheres cancel, Kelvin cancels. That gives liters per mole. You got to make sure the units work out. So 848 times 0.08206. Divided by 248. 0.28. 0.28. 2805 liters per mole. Yeah. You know, although the temperature is very high, we expect a larger volume, but then the pressure is somewhat extreme, 248 atmospheres. So that really squeezes the gas down. Under normal conditions, it's closer to 25 liters. Here, we don't even have a quarter, just a little over a quarter liter. That would be the molar volume. So, we're going to just use dimensional analysis for this one, 9.16 times 10 to the third grams of ammonia. And then do a gram to mole conversion. Nitrogen, 1401. 3 hydrogen, we made 303. It gives us 1704. So a mole of ammonia weighs 17.04 grams. And so the grams of ammonia cancel, and that takes us to moles. Then we go from moles of ammonia to moles of nitrogen. The mole ratio is given here. It's 1 mole of N2 for every 2 moles of NH3. NH3 cancel. And then we'll go straight from moles of N2 to liters of N2 using the molar volume here. This molar volume is good for any gas. The molar volume is going to be 0.2805 liters per mole. This is going to be for gas at 248 atmospheres and 575 degrees C. It's only valid under these conditions. If we change the conditions, the molar volume will change as well. So what we get here. So 9.16 times 10 to the third divided by 1704 divided by 2 times 0.2805. So under these conditions, we should have 75.39 liters of nitrogen gas. To react. So assuming I didn't make any errors, that should be calculator errors. That should be okay. Setup is fine. Okay, any questions on this problem here? All right, let's take a look at number 39 next. When properly detonated, ammonium nitrate explodes violently, releasing hot gases. Ammonium nitrate, is that expected to be unstable? What makes ammonium nitrate so unstable? What makes ammonium nitrate so unstable? It has to do with redox properties. What are the redox properties of ammonium nitrate? This is, there are lots of examples of ammonium nitrate. One is the Texas City. Remember Texas City? Grand Camp is the name of the ship. Actually, 2 ships. One was the Grand Camp. I forgot the name of the other one. Anybody recall? The ships were filled with ammonium nitrate. Makes ammonium nitrate so unstable. Can you look at the oxidation states and tell me?
Kelvin, but 447 Celsius, the pressure at 896 torques. I don't know what to do with it. But it's final temperature pressure. So,
Did I talk about pressure fraction, volume fraction, mole fraction, that kind of stuff? Did I talk about air? Dalton's law? Does that stuff ring a bell? No? Yeah, we'll look at it in just a sec. We'll see what to do with it. But just as far as little bits of review for the final exam, was anybody able to get the oxidation states? This ammonium nitrate? Sometimes it helps, let me give you a hint, sometimes it helps to split it up into ions rather than look at it as a compound. And so try, if you're having trouble getting the oxidation states, try splitting it up into the ammonium ion, and just look at the ammonium ion, and then the nitrate ion, and just look at the nitrate ion alone and the ammonium ion alone, and see if you can get the oxidation states, because the oxidation states will be the same in the compound as they are in the ion. Review is often, a huge job, review for final or review for a major test. And so it's good to get started earlier. Earlier is better. Start reviewing this stuff. You try to cram everything into one night. It's super high stress. I used to do that all the time. Maybe I still do. Try to avoid it. Okay, we'll just go through it for ammonium nitrate, just as a little side over here. So one thing you could do is just split it up to the ammonium ion. And so over here, hydrogen would be +1. We have 4 of those. This whole thing carries a plus charge, so nitrogen has got to be -3. -3 plus 4 gives us +1. So this nitrogen we would consider electron rich. Nitrogen likes 3 electrons, then it has an octet. Nitrogen needs 3 electrons in an octet. Then when we look at nitrate has a net negative charge. The oxygens are -2 each, so it's -6. That means this nitrogen's +5. That means this nitrogen's lost all its valence electrons. And so you have one nitrogen that's +5 and another nitrogen that's -3, and they're right next to each other. Is that a stable situation? No. One nitrogen's very rich, the other is very poor. So this compound is very interesting because this compound has both the fuel and the oxidizer in the same compound. Ammonium's the fuel, the oxidizer is nitrate. And so this one you don't need any oxidizer like air or anything like that. Do it. Now, number 39, we need to know about gas mixture. So I probably forgot to talk about this, so let me talk about it now. There are 3 ways, actually, 3 common ways we think about gas mixtures. Maybe 4. This is not all in your book, but it's important to understand in answering this particular question. Percent by mass. Let's look at air. You know, do you know what the percent by mass oxygen is in air? Percent by mass. So if I had 100 grams of air, in 100 grams of air, how much of that is oxygen? How many grams? So let's take a look. Percent by So I searched out percent by mass air. So the gaseous composition of dry air popped up. This is the first link. Is this percent by mass? No. That's not percent. What is that? That's mole percent. In terms of mole percent, I said that air is about 20% oxygen, 80% nitrogen. This is oversimplifying thing. This is dry air. It's more like 21% oxygen, 78% nitrogen and other stuff. But 20-80 keeps it easy for me to talk about. There are other components to air as well. You know, we have some argon, carbon dioxide. Carbon dioxide levels vary, you know, depending on where you're at. Neon, helium, methane, krypton, hydrogen, nitrous oxide, xenon, ozone. Of course, there's water vapor in air too. This is totally dry air here. There's going to be some, but the water vapor amount depends on the humidity. Humidity is all over the place depending on if you're close to body of water, what coast you're on, east coast and west coast, and so on. These are pretty much trace to ozone, carbon monoxide, sulfur dioxide. Actually, on Hawaii, this is probably very high right now. Hawaii, sulfur dioxide is very high. Oxide of nitrogen, ammonia. But I wanted percent by mass. I didn't want percent by air. So I said percent by mass air by mass. So that was the first link. Let's hit the second one. There's a mole and mass ratios. Okay, here we go. These are what we call mass fractions. These are over 1. So this would be 23.3% oxygen by mass, 76.7% nitrogen by mass. So percent by mass is close, but it binds this oxygen. Oxygen's heavier. It's a little heavier here. So that's where we go. There's a percent by mass. Let's see if we have more percent. If we look at percent by mole, percent by moles over here, this is the fraction. So this would be 21% oxygen, 79% nitrogen. So we can either express things in terms of mole fraction or mass fraction, or mole percent or mass percent. Let's take a look at this. This is mass percent. right, what's common though for air is mole percent. So percent by mass, we could do percent by mole. And percent by mass is not common for air or gases. Percent by mole, this is common for gases. So let's look at air. Air is, let's just keep it simple. 20% oxygen is by mole. 80% nitrogen, mole percent. That means if I had 100 moles of air, 20 moles of it would be oxygen, 80 moles of it would be nitrogen. Another way of visualizing this is like this. As far as molecules go, if I had a box, then 80% of the molecules in the box would be nitrogen, a box of air. So if I had 100 molecules, 80 would be nitrogen, and then 20 of those molecules would be oxygen. If I have a different color for oxygen. So, orange will be oxygen in this case. Black will be nitrogen. All right, this is a percentage, what we call a percentage. We also have a fraction. As far as the fraction goes, then 20 out of 100 will be O2. 20 moles out of 100 moles, 20 molecules out of 100 molecules. 80 out of 100 will be N2 by mole, or molecule. The fraction can be written like this, 0.20 or 0.80. This is also called a fraction. This is divided by 1. So this is out of 1. 0.80 out of 1. But usually we leave off of 1. That's for a fraction. The percent by mole. Dalton's law looks at this mixture in a different way. This mixture is going to consist of the nitrogen, which is the black, and the oxygen, which is the orange. And so if we look at the pressure fractions, that would be Dalton's law. Pressure. All right, so what we're going to have is we're going to have this. The pressure percentage will be this. If we think about this box and we just look at the collisions between the black and the wall versus the orange and the wall, then 80% of the collisions will be black molecules with the wall, 20% of the collisions will be orange molecules with the wall, and therefore 20% of the pressure is going to be generated by oxygen, by pressure. And 80% of the pressure is going to be generated by nitrogen. Pressure fraction. So, in other words, the mole fraction is equal to the pressure fraction. Mole fraction is equal to the pressure fraction. And so the way we think about this by Dalton's law is this. Let's say I have a box here. This box is a 100 liter box of air. And this air, let's say, is at 1 atmosphere. All right, if we visualize this using Dalton's law, then I have how much nitrogen? Well, I have 100 liters of nitrogen. Actually, I should do 1.00. And so let's just take out the nitrogen, put it in a 1 liter box. There's going to be no orange molecules here, so the only collisions with the wall will be the nitrogens. And so if I had 1.00 liters of nitrogen, then the pressure is going to be just 0.80 atmospheres. It would be 80% of the pressure because 20% of the molecules are missing out of this box, so 20% of the molecules would be the orange molecules of O2. And so what we'll do is we'll put those in a separate box here. And so in the separate box, this is going to be 1.00 liters of O2. But, you know, the O2, there aren't that many molecules here of O2, so we're going to generate a lot lower pressure. So this is going to be 0.20 atmospheres. And so what Dalton's law says is that if I take the partial pressure of nitrogen, 0.8 atmospheres, and add that to the partial pressure of oxygen, 0.2 atmospheres, I'll get the pressure of the mixture. In other words, Dalton's law says that the P total, 1 atmosphere, is equal to the pressure of the nitrogen plus the pressure of the oxygen. The P total would be for air, the mixture. And so the pressures are additive. But a strange thing happens here. The strange thing that happens is this. The volumes are not additive. Because what I got to do to make this work is this. 1 liter of nitrogen plus 1 liter of oxygen equals how many liters? So if I take a liter of nitrogen and add that to a liter of oxygen, how many liters do I get? You'd expect 2 liters, but I don't, because I got to put these all in the same box. And so what I have to do is I take 1 liter of nitrogen and combine it with 1 liter of oxygen into a 1 liter box, and that gives me 1 liter of air. And so the volumes are not additive. The volume of air is equal to the volume of nitrogen, which is equal to the volume of oxygen. In other words, volume is what we say constant. Volume is constant. The volume doesn't change. The volume is always the same. So if I take 1 liter and 1 liter, it gives me 1 liter. The volume never changes. This is what we call Dalton's. So what we can do is we can visualize this mixture here that we were looking at by Dalton's. We have a mixture of 1 part N2O and 2 parts H2O gas. And so there are 2 parts plus 1 part gives us 3 parts total. And so as far as mole fraction goes, 1 out of 3 moles is N2O, 2 out of 3 moles is H2O. And so that means that this is 1/3 nitrous oxide, 2/3 water. It's a mole fraction. Now we can do the same thing with the pressure. That means if 1/3 of this mixture is nitrous oxide, then that means 1/3 of the pressure has got to come from nitrous oxide colliding with the wall, and then 2/3 of the pressure of this mixture has to come from water molecules colliding with the wall. And so out of the total pressure here of 896, 1/3 of that arises from nitrous oxide, 2/3 of that arises from water. Does that make sense? Because we're looking at a mixture of nitrous oxide and water in a 1-to-2 ratio. Do you guys see that? Or should I write it down? Or you see it? Maybe I'll write it down, but I'll write it down after I finish air. I'm not done with air. The reason we like things in mole fraction is because mole fraction is equal to the pressure fraction, according to Dalton's law. Whereas the mass fraction doesn't do that. The other reason we like mole fraction is because the mole fraction is equal to the volume fraction. And so there are 2 ways of visualizing the exact same. One, we visualize it with pressure, it's Dalton's. Or 2, we visualize it by volume. This is called Avogadro's. And so what we can do is we can visualize this exact same mixture differently according to Avogadro's. Since I ran out of room there, I'm going to write Avogadro's over here. If I take 1 liter of air, how much nitrogen do I have? According to Dalton, if I take 1 liter of air, I have 1 liter of nitrogen at 0.8 atmospheres. If I look at the exact same mixture and I have 1 liter of air under Avogadro's, then I don't have 1 liter of oxygen. Under Avogadro's, I have 0.80 liters of oxygen. And so what we're going to do in Avogadro's is we're going to squeeze the box down a little bit. Why do we squeeze the box? Not oxygen, nitrogen. Why do we squeeze the box down a little bit? We squeeze the box down a little bit to maintain a steady pressure. And so this is going to be 0.80 liters of nitrogen at 1.00 atmospheres. And so I'm going to have 1.00 atmospheres of nitrogen, but the box is going to be smaller. For oxygen, I have so few oxygen molecules that I have to really squeeze down the box to generate that kind of pressure. And so the box for oxygen, to generate the same kind of pressure is going to be 0.80 liters. Not 0.80, I keep saying 0.20 liters of oxygen. But I'm going to have 1.00 atmospheres. And so for Avogadro's, the volumes are additive. V total, which is for air, is equal to the volume of nitrogen plus the volume of oxygen. However, P, the pressure of the total that is air is equal to the pressure of nitrogen, which is equal to the pressure of oxygen. So we call this constant pressure. So we can visualize the air as a constant volume mixture or a constant pressure mixture. If we visualize this as a constant volume mixture, then we're visualizing it like this, Dalton's. So, how many liters of nitrogen do I have? I have 1 liter. This nitrogen fills this box. How many liters of oxygen do I have? I have 1 liter. How many liters of air? I have 1 liter. It's all in the same container. That's Dalton's. When I visualize this using Avogadro's, it's not that way. It's how many atmospheres? How many atmospheres of air do I have? 1 atmosphere. How many atmospheres of nitrogen do I have? I have 1 atmosphere. How many atmospheres of oxygen do I have? 1 atmosphere. So if I take 1 atmosphere of nitrogen plus 1 atmosphere of oxygen, I get 2 atmospheres of air? No. 1 atmosphere. It's because of the way they add up. Now when I add these two up, the pressure of each decreases. And so let's go to problem number 39 here, and we can visualize that gas mixture either way. I have a gas mixture that consists of nitrous oxide, N2O, and H2O, and it's a 1-to-2 ratio. And so that means I have, as far as fractions go, it'll probably be easier. 1/3 mole fraction of nitrous oxide, 2/3 mole fraction by mole of water. So that gives me a choice. I could either visualize this as a Dalton's or I could visualize it as an Avogadro's. So which one do you want to do? Well, actually we could do both if you want. Do both for practice. And so, well, this is more practice for Chem 1A. And this Chem 4 focuses on Dalton's. Maybe we don't need to do this. Maybe we should just visualize it as a Dalton's mixture. But anyway, I have 82.3 liters at 447 degrees C. So we don't want to change the temperature, because if we start changing the temperature, the molar volume changes, and we have a headache. Then we have 896 torr. So why don't you do this for me? Why don't you do this? Visualize this as a Dalton's first, and tell me what you get, and then visualize it as Avogadro's and tell me what we get. Okay. So let me give you a